Hi everyone, this is Manas, your friend and tutor, and guys, I'm back with another video on deflection of beams, and you know what the topic is. It's moment area method. So here is the problem in front of us, and you can clearly see that we've got a couple acting at point A, and we've got obviously two supports, a hinge support and a roller support. What we need to do is we need to find the displacement at C, or you can also say that deflection at C is supposed to be calculated. How to approach? Well, whenever you encounter any problem on moment area technique, what you need to do is make the elastic curve first of all. Okay, so obviously you see the nature of this. See the nature. The nature is sort of a sagging nature like this. It will try to bend the beam in this fashion, isn't it? And hence, what I'm assuming is elastic curve would be looking something of this sort. This is the profile that it might have. Let's say that this point is C. Okay, let me now place tangents at A, B and C. So here is the tangent at A, that's at B, and that's slightly uphill at point C. Now, what are we supposed to calculate? The displacement of C. This distance is what we want. Let me just mark it up, this YC, right? Now what to do? Just try to extend this tangent at B, extend it, right? And vertical displacement, just listen to what I have to say. Vertical displacement of the tangent at C with respect to tangent at B, this distance. Vertical displacement of the tangent at C with respect to tangent at B, that is TC to B, TCB, right? Again, vertical displacement of the tangent at C with respect to the tangent at B, that is TCB. That's it. Similarly, in the same pattern, this is tangent at A. Okay, if I draw a vertical line, then that would qualify as the vertical displacement of the tangent at A with respect to the tangent at B. That's what you call TAB. So that was all about what do you call elastic curve, a bit of construction with respect to the tangents. And now let me just try to simplify stuff, and let me also frame the compatibility equation. So just watch this. Let us say this is point P, this is point Q, this is point R. What you can see over here is two similar triangles, that is BPQ and triangle BAR. What do they exactly mean and what exactly do they convey? Let's start. So the first thing is, if you watch, this PQ can essentially be written as the algebraic sum of PC plus CQ. PQ is equal to PC plus CQ. Watch. PQ is equal to PC plus PQ. And you can clearly see that this PC is YC and CQ is TC to B. YC, so that is essentially equal to YC plus TC to B. Right? Now, how to get the value of PC? Not PC, but how to get the value of PQ. Just watch. You can clearly see that these are two similar triangles. Okay. One is BAR, other one is BPQ. Watch. What do we need to work out? We need to work out PQ. So for two similar triangles, you can apply the ratio of side property. That means PQ divided by AR is equal to BP divided by BA. Here we go. PQ divided by AR. PQ divided by AR is equal to BP divided by PQ divided by AR is equal to BP divided by AB or BA, whatever. BP divided by AB, let's say. So what do we want? We want PQ. Okay, alright. So just watch this. This is going to be fairly simple. PQ divided by AR. What is AR? Do we know what AR is? It is TA to B. TA to B. A to B. Anything else? We've got BP. What is BP? BP is L by 2 and AB is L. The length of the beam is L. So L by 2 divided by L. BP L by 2 divided by L. You just need to solve this equation and that's it. L and L will cancel out. So what remains? What remains is this. PQ is equal to T A to B with divided by 2. And let me just frame our final compatibility equation. So let me put the value of PQ from this here. Okay, so let's do this. PQ is nothing but T A to B by 2, and that's equal to YC, deflection at C, displacement at C, whatever, plus T B to C. What do you want? You want this displacement at C. How can you do this? So just shift YC is equal to, obviously now, T A to B divided by 2 minus T B to C. So the objective is very clear. The objective is very clear. In order to get the value of YC, you need to work out T A to B and T B to C. Since both of them are displacements, you need to apply the displacement theorem, right? But for applying the displacement theorem, again, you need to know how the M over EI diagram looks. And in order to know what the M over EI diagram is, you first need to know what are the bending moment values. And in order to get the bending moment values, you need to find the reaction at the supports, that is at A and at B. Okay, so the first thing, guys, which you all should write down, please note this thing down. Pause the video, note all of these things, because I'm going to be rubbing it off, right? There are a whole lot of calculations. Okay, awesome. So this essentially is our master equation. That is our master equation, or the compatibility equation, whatever you can say. Let me just try this master equation. And now it's very clear what all things we need to work out. We need to work out TAB, we need to work out TBC. Okay, and essentially we need to apply theorem 2 or the deflection theorem of the moment area technique. All right, now let's move to the next slide and let us try to work out the reactions at A and at B. Okay, at the hinge and at the roller support. Here we go. Just watch. Let me make this figure once again. Here we go. Now, what I have done, I have removed the support and I have replaced it with a reaction. Reaction at A, fair enough. Similarly, I have removed this roller support and I have got a reaction at B. Okay, what I want are the values of RA and RB, and how can I achieve them? It's going to be very simple. You just watch. What you can do is, you can do summation of moments, let's say about point A is equal to 0. And if you watch this RB, isn't this anti-clockwise? With respect to A, with respect to this point, this is anti-clockwise. So RB multiplied by L, that's positive for you. Okay, so anti-clockwise positive, RB times of L. What else? And also you've got this bending moment, right? This moment over here. Nature is clockwise, obviously. Clockwise, we take it as negative. So minus M naught is going to be 0. And from this equation, you can say that the value of RB, which we have got, is M naught over L. It's that simple. In the same fashion, you can apply another equation of statics. Summation of all the forces in y direction is equal to 0. And that says that RA, well, it is upwards. RB, it is upwards. And that's it. There is no other force to work with. RA plus RB is going to be equal to 0. Therefore, RA is going to be equal to minus of RB, and you know what RB is. RB is minus, not, it is M naught over L, so this is going to be minus of RB, minus M naught over L. Now, that's over. Now we shall work out bending moment values. Okay, moment values, not just moment values, but this is the these are the bending moments values which we need to work out. Bending moment values. All right, how to approach? Just take a look at this RA. What is RA? It is negative. The direction that I chose, that means the direction that I chose was wrong. RB is positive, that means the direction of RB that I chose was correct. Upward direction which I chose initially for RB was correct. But this answer of RA is negative, that means the direction that I chose was wrong. Therefore, this RA should be in the downward directions, right? And finally, it would look something like this. Let me reverse the direction. The magnitude of both the forces, both the reactions, that is RA and RB, are same, M naught over L. And finally, when you reverse this RA, this is what you are going to get. M naught over L, this is M naught over L in the upward direction. This is M naught over L in the downward direction. Let us go back just a second. Okay. Now just think about this. This is a couple, isn't it? clockwise, and this is the response from the supports. What is the nature? Anti-clockwise, isn't it? A clockwise couple being countered by an anti-clockwise couple, isn't it? So why am I saying it? This is a couple because you can clearly see that these are two parallel forces. Not parallel, these are two anti-parallel forces. They are separated by some distance of L. So m naught by L multiplied by this L will give you the couple. It's magnitude, that is m naught, simple. So this is equal to this. Okay, so the active couple and this is the reactive couple, you can say that. Don't get into the couple business. What we now need to do is we need to work out the bending moment values at A, at C and at B. So it's quite clear that the bending moment at A is equal to, well, see, plus m naught and not minus. Why? The reason being very simple. If you watch, this is sort of it's called sagging bending moment. Why? Because initially the beam is straight. It is acting in such a manner, it will try to bend the beam in this fashion. This is a clear-cut case of sagging, and sagging, we apply a positive sign. That's why moment at A is m naught. What about moment at C? How much is moment at C equal to? So if you watch, you can essentially calculate the moment at C by two ways. Let me tell you. Here we go. So this is moment at C, and considering the right portion also, you can find the value. Now if you watch, if you consider the left portion of the beam, you've got a force in the form of m naught over L, and then you've got a couple. How much? That is m naught. Yeah. Similarly, if you consider the right portion of the beam, that is m naught over L. This one, that is m naught over L, and obviously this is L by 2, and this is L by 2, and this is the section. Okay. So we are interested in calculating MC, right? So if you consider the right portion of the beam, let me just do it here. If you consider the right portion of the beam, first of all, let us take this L portion, left portion. So this force will try to bend the beam in this fashion, isn't it? What is this? Clear-cut case of hogging minus, that is going to be m naught by L multiplied by L by 2. And if you watch this couple over here, this moment over here, it will try to bend the beam in this fashion, inwards, in this fashion, sagging. So plus m naught. On solving this, L and L will cancel out. M naught minus m naught by 2. This will give you the value as m naught by 2, simply. So this is the bending moment when you consider the left portion or portion of the beam which is to the left of C. Similarly, this is to the left of C. Similarly, you can calculate the bending moment when you consider the portion of beam towards the right of C. These are all basic stuff. This is something which you have learned in shear forces and bending moments, I am very much sure, right? And this is where it is getting revised. So this is fairly simple. This force will try to bend the beam in this fashion. What is this? Sagging case. That means a positive sign. Name of the force is m naught over L multiplied by L by 2, and there you go. The value that you've got is m naught by 2. Simple. M naught by 2, m naught by 2. Does not matter which portion of the beam you consider. Always you will see that you are going to get the same value. And finally at B, you can check it out. It is going to work out as 0. If you want to see, please first of all note these things down. Pause and note. Done. Let me erase. Okay. So the moment at C worked out as m naught over 2, and the moment at B finally will work out as 0. You can check it. You can even check it. Just take a look. What do we need to find? We need to find the moment at B. Just take a look. This is clockwise. Okay. The nature is it will try to bend the beam in this fashion, sagging case. So obviously this is going to be plus m naught, right? Then you've got this. Okay. So it will try to bend the beam in this fashion, hogging case. Okay. So that is going to be minus of m naught over L multiplied by L. It's that simple, right? Minus of m naught over L multiplied by L. And apart from that, we've got something more. Where is this? Yeah, that's it. That's it. There isn't anything. So when you want to find the moment at B, you have to consider this couple and this force. That's it. And obviously they cancel each other out. And obviously it is going to be 0. And that is the reason I have written 0 over here. Now we know what the values are. And we want to make the corresponding M over EI diagram. How can that be made? And for that, please note these things down. I'm going to be rubbing it off. Pause and note. Okay. M naught by 2 and 0. Okay. Let's begin. Okay, let me plot the values. At A, bending moment at A worked out as simply M naught. Bending moment at C worked out as M naught over 2, and at the same time bending moment at B was 0. So let us plot. What we need to do is make the corresponding M over EI diagram. That is the diagram, and just watch. At A, the bending moment is M naught. So this is M over EI diagram. Divide by EI. M naught divided by EI. This is going to lie somewhere here. So that's A, that's C, and that's B, right? That's M naught over EI. Similarly at C, exactly half. M naught over 2 EI. Done. And at B it's 0. So when you try to join all these points, one single line will be through all of them. That's it. Now what? Now let's get back to business. Let's get back to business, because for calculating both of these T's, what we need is we need to apply the second moment area theorem, that is the displacement theorem. Okay, let's find TAB. Okay, you need to find TAB first of all, and then only you can proceed. Okay, how to go ahead? Let's find TAB. Just watch. TAB, how do you read this? TAB, vertical displacement of the tangent at A with respect to the tangent at B, right? Let me get back to that elastic curve. Where is it? This is slide 21. That was 19, I guess. Okay. We want to find this vertical displacement. Fair enough. So, vertical displacement of the tangent at A with respect to the tangent at B. This vertical displacement can only be calculated by taking the moment of the area between A and B. Let me just write the formula. TA to B from theorem 2. TA to B is equal to x bar multiplied by area, not just any area. What is this area? We need to go back to the moment area diagram. Here it is. Okay, what is this area? A dash B A dash B A, right? Once again, what we are trying to do is we are trying to find the vertical displacement of the tangent at A with respect to tangent at B, and this essentially is equal to x bar. Okay, this is the centroid's location multiplied by the area between A and B. So the area between A and B is this much. Here is the shaded region. This is the area that you need to work out. And as far as this centroid is concerned, this has to be measured, or let me just write this. The centroid has to be calculated or located with respect to this, that is A. Where do you want to find the vertical displacement? At A. That's why you have to take the moment of that area with respect to A. Simple, just do the math. This is going to be very simple. What is x bar? Let me tell you. Watch this. The centroid of a right angle triangle. Okay. Remember, if the base is B, it's going to be B by 3. Here the base is L. This is going to be L by 3. That's simple. Okay. With respect to A. Remember, not with respect to B. If it was supposed to be calculated with respect to B, then it would have been 2L over 3. Anyways, this is L by 3 multiplied by area. It's a triangle, half of base. Base is, it's clear cut. Very simple. This is base is L and height is M naught over EI. Fairly simple. L M naught over EI. Very simple math. TAB has been calculated. This is equal to M naught whole divided by 6 EI. Now let's find TC to B. TC to B. TC to B. Okay, by applying theorem 2, product of centroid's location multiplied by the area. What area? Not just any area, area between C and B. And let me show you what that area is. Area between C and B, here it is. Okay, C dash CB, C dash CB, and there you go. X bar, well, X bar has to be measured from the C, okay, with respect to C. Here it was with respect to A, here it is going to be with respect to C. So with respect to C, the distance is, well, L by 3, remember, but this L has become L by 2. L by 2 divided by 3 would become L by 6. Fairly simple, L by 6 multiplied by area is half of base into height. Base is L by 2 and height, let me check, is M naught over 2EI. This is M naught over 2EI. So 6 2 is 12, 12 2 is 24, 24 2 is 48. So T C to B has worked out as M naught L square divided by 48 EI, and even here M naught L square. So now let's apply the finishing move. Here we go. Value of YC. YC is equal to TAB over 2. TAB is this much divided by 2. This will become 12. This is M naught L square over 12 times of EI, then minus TCB, C to B, M naught L square upon 48 EI. This is M naught L square upon 48 times of EI, and there you go. This is the final value. YC would be working out as M naught L square upon 16 EI. Very simple math. That's it. That's it. So guys, that was all for today. I'm going to see you again in the next video. Until then, take care. Have a nice day. Keep learning. Keep watching. Thank you.